Look at this turbulent cascade. It is chaotic, yet highly structured across multiple interacting levels of organization at once. When we model motion like this, we usually rely on traditional mathematical abstractions, specifically scalars and vectors. We treat them as entirely context-free. A scalar records how much of something there is. A vector records how much and in which direction. Both assume the surrounding environment is irrelevant to the value itself. That abstraction fails when the environment dictates a value's meaning. The abstract ideal maps the number 5 to stones, meters, or energy, but in complex reality, these vector arrows are trapped within an anisotropic boundary layer, influenced entirely by their surroundings. In anisotropic media, turbulent flows, or quantum systems, magnitude alone cannot specify a quantity. The value is inextricably linked to the scale of measurement and the underlying symmetry that governs it. Addressing this ontological limit requires a specific formal mathematical object, the Noetherian Finsler number, or NFN. This diagram represents the calculus of closure memory. It defines Noetherian Finsler numbers as a new class of formal objects that function as closure coordinates. NFNs complete standard mathematics by ensuring the equations themselves remember the physical conditions necessary to preserve their own identity. In this framework, standard vectors are reduced forms of NFNs. A vector works, but only if we assume the scale and invariant structure of the system are entirely fixed. This latter illustrates where physical data is lost. We build from a scalar to complex and up to a vector. Ascending through Finsler and Noetherian objects reveals the gap to the full NFN value. Downward projection incurs a quantifiable error, calculated here as projection cost. To eliminate projection cost, the NFN formalizes 4 parameters into one object: M, D, S, Q. M and D represent magnitude and directionality, inheriting Finsler's directional dependence. S defines scale, anchoring the value to a regime. Q is the conserved invariant, the closure charge preserving the system's structure. Projecting data down to a scalar or a vector fails when the scale and conserved identity are the specific parameters keeping the physical system coherent. Because NFNs carry this extra information, they cannot be added or multiplied using standard arithmetic. They require closure-compatible superposition. Any interaction requires a strict prerequisite. As the left panel illustrates, 2 NFNs can only interact by meeting a shared closure condition. Moving to the middle panel, NFN multiplication simultaneously couples their magnitudes, directions, scales, and invariants. Finally, the right panel isolates the non-commutativity equation. This defines path-dependent closure. In this framework, A times B does not equal B times A if the order of interaction changes the underlying structure of the system. NFN algebra is directional. The specific order of operations actively dictates whether a system's identity survives an interaction or collapses. So how do these closure coordinates actually measure physical space? Standard Riemannian geometry maps space using a metric that depends entirely on physical position. Mapping direction and identity simultaneously requires the mathematical leap shown in this metric tensor equation. Beneath the tensor, the standard position variable, x, is paired with a direction variable, y, providing Finsler's directional dependence. The invariant structure term, q, adds the exact Noetherian contribution. This metric ties geometric distance and energetic cost directly to the conditions required for an object to preserve its continuous identity. If identity is defined as bounded persistence, how does an object physically move through phase space? This chart contrasts 2 trajectory approaches. On the left, taking the shortest physical distance is destructive because it ignores internal invariants, colliding with obstacles. On the right, the invariant q is preserved as it navigates a protected margin, driven by the phi constraint equation below. The phi term acts as an active constraint on the geodesic, forcing the trajectory to curve around disruptions. In NFN geometry, physical systems dynamically navigate reality along paths of least closure disruption, protecting their defining structure, even when it requires a longer path. Observe a living cell membrane actively filtering molecules. It constantly exchanges matter, yet rigorously preserves its intact vibrating cellular wall. NFN theory models the cell membrane as a mathematical boundary using the NJ equation. The scalar flux, J, and normal vector, N, are constrained by the membrane scale, S-mem, and cellular identity, Q-cell, acting as a boundary closure operator. In the quantum realm, standard scalar projections fail to capture reality. The wave coherence zone introduces the N-psi equation. It binds amplitude, phase, measurement scale, and invariant symmetry into one object, tracking exactly how coherent states survive physical transformations. Noetherian Finsler numbers provide a precise, required coordinate calculus for complex systems, where dropping context breaks the mathematical model.